So first things first, be sure to follow Fiveable on all social media stuff and all sorts of, YouTube, Twitter, Instagram, to be sure to know when, when new live streams are coming up and when new events are happening, especially pertinent to AP Chem. All right, so tonight's topic that we're really going to be talking about in general is going to be just moles and molar mass. So things like converting from particles to moles, from moles to grams, and how to calculate the molar mass of certain particles, certain molecules, certain things like that, and how to apply that to what you'll be learning in the future. Because this type of stuff right here with like moles and molar mass, this isn't really what you're going to be directly tested on the AP exam. It's going to be more, how do you apply this topic to things like stoichiometry, which we'll be learning about in the future, or how does this, act with certain things with reactions. So that's really the point of why you need to know this and why this is so foundational to what AP Chem is all about. So really, if you understand this, it's really important to practice as much as you can and to really get to it in the future. And to the people just right now joining, tonight we're going to be going over moles and molar mass, and just you can drop any questions you have in the chat and stuff like that. Just let me know. You guys can hear me. If I ever cut out or if there's any audio issues, video issues, just let me know. All right. So the first thing we're going to be going over is really just the definitions, right? What is a mole? What do those things mean? So really, the official definition of the mole is the SI unit, so the International System of Units for the amount of substance. And that's kind of an abstract idea, right? When you think of amount of something, it's kind of weird to think about. When you hear amount, you might think weight, mass. You might be thinking something other than that. But with amount, it's really just a number of something. It's kind of a very weird, abstract concept to kind of wrap around your head. But according to the IUPAC, which is a big chemical organization, they're the people who name all the elements and stuff like that. Their definition is that 1 mole of something contains exactly 6.02214076 times 10 to the 23rd elementary entities. So that's kind of a really weird definition, but basically all it states is that 1 mole of something means you have this number, this 6.022 times 10 to the 23rd of that thing. So there was an old definition of the mole, which was the number of atoms that was in 12 grams of carbon-12, but now it's been changed to be exactly that number of something. And so this number is, it's called Avogadro's number. It's named after the guy that discovered the number and that calculated the number. And really just what it boils down to is that 1 mole of something is equal to 6.022 times 10 to the 23rd of that something. So it's kind of a simple topic, but it can be really difficult to wrap your head around, maybe because of the number, maybe because of how abstract that idea is. So what I like to do is always, weigh it against something that we know. We know what a dozen is, right? That's something that really, I think most teachers will do this. They'll compare a mole to a dozen. So with a dozen, you have 12 things, right? You can have a dozen apples, a dozen oranges, a dozen, dozen loaves of bread. I don't know why I'm thinking about food, but you can have a dozen of anything, right? If I said, I have a dozen pencils, that means I have 12 pencils. So if I say I have a dozen, if I have a mole of pencils, the same thing applies. That I have, it's just instead of being 12, it's 6.02 times 10 to the 23rd of that thing. So do you guys understand that? Does that make sense to you guys? Drop in the chat if I'm moving a little fast, or if I'm, just let me know, because I can see the chat. So you guys, can feel free to chat in there. But if you have any questions, feel free to drop them. And so really, you can have something that I like to think about is that you can have a mole of apples just like you can have a dozen apples, right? So if I have a dozen apples, I have 12 apples. Whereas if I have a mole of apples, I have 6.022 times 10 to the 23rd of apples. And the way we get that number, it's kind of a lot of complicated calculations involving the number of particles in a certain amount of things. And that's really where it comes from. But really, what it boils down to is what I've been repeating this whole time, that the dozen is the amount of substance that contains 12 entities, whereas the mole is the amount of substance that contains this Avogadro's number of entities, right? So really, while we know what the mole is, it doesn't really make sense until we try to apply it to something like converting between particles and moles, right? So the first thing we're going to do here is just do a quick review of dimensional analysis, right? How do you convert from between units? How do you convert from feet to inches? And then from there, we can see how we can convert from moles to atoms or particles. So really, when we're looking at dimensional analysis, our major, this isn't a formula, but the major way you set it up is that you have your starting unit times some conversion factor is going to equal a new unit. Right, what's going on? Right. So if we're converting, let's say, 4 feet to inches, the conversion factor that we're looking at is how many inches there are in a foot, right? And then these feet cancel out, and we're left with our new unit because of this conversion factor. So our goal in these problems is to convert between atoms and moles. You know, if I have 2.6 moles of iron, like this problem says, how many iron atoms are actually there? Right, so that's really the major type of problem that you're going to be seeing. So let's just kind of look at how we're going to do this problem. So remember, we have our starting unit times our conversion factor equals our new unit. So we can fill in this starting unit and this new unit here. And we have 2.6 moles of iron, right? That's right here in the problem. And we want atoms of iron, right? It again tells us what we want. So really what we want to find out is what is that conversion factor? So you guys have, any guesses on what that conversion factor could be? If you know, drop it in the chat. What is that number that you have to multiply by or divide by in order to get to your new unit? Yeah, exactly. You have an Avogadro's number of atoms per 1 mole of some element. It's perfect, right? And that's because of the definition of the mole, right? If you have a mole of something, that means that you have 6.022 times 10 to the 23rd of that something. So if we look, we can see that when we set up our problem, when we have the unit we want over the unit we have, some number of atoms per 1 mole. Well, we know that if we have a mole of atoms, we're going to have Avogadro's number of that atom. And so we're going to replace that X right there with Avogadro's number. And that's how we would complete this problem, where you have 2.6 moles of iron. And then by doing dimensional analysis and by making sure that we know that these moles are going to cancel out, we'll be left with the number of atoms of iron. So yeah, when we do this problem, we end up getting 1.6 times 10 to the 24th atoms of iron. And that kind of makes sense, right? If you have 2.6 moles of something, it means you're going to have roughly 2.5 to 3 times of this number, which is roughly something times 10 to the 24th. So really, you can definitely tell when you are really off with these types of problems. It's really easy to screw them up too if you put it into your calculator wrong or something like that. But there's always you can always tell when you screwed something up because you'll get an absurd answer. So for example, just let's try to do this problem. And this is pretty much the exact same problem as before, just with different numbers. But just determine the number of atoms in 2.5 moles of zinc. Right, so let's think, what is the first step of this problem going to be? We want to set up our dimensional analysis, and then we want to multiply by our conversion factor again, which, as Owen said, is Avogadro's number over every mole, for every 1 mole. So if we look at this, we see set it up exactly like the last problem, where we have 2.5 moles of zinc, and then we're going to multiply by Avogadro's number to get that 2.5 moles of zinc has 1.5 times 10 to the 24th atoms of zinc. Anyway, so with this problem, we can see that it basically follows the same structure as the last one, right? We just have a number of moles of zinc, and we're going to multiply it by Avogadro's number in order to convert. All right. However, this can be flipped on its head. Right? You might be told that you have 5.75 times 10 to the 24th atoms of aluminum, and you need to convert that to moles. So would you wouldn't use the same conversion factor. So what would you do? What would be your conversion factor to multiply by if you were to do this problem? Right. So what would be if we set up this problem just the same, right, where we had 5.75 times 10 to the 24th atoms, what would our new conversion factor be so we can get to moles? Exactly. Yeah. You're going to basically just flip your conversion factor, right? Because when you have atoms, you want atoms on the bottom of your fraction so that they cancel out, and you end with moles. Just be sure to, when you're doing these types of problems, don't just write the numbers. Be sure to write the units out, not just for the sake of the problem, but also it really helps you be more clean and more organized with your work. So we can see here we have 5.75 times 10 to the 24th atoms of aluminum, and then we flipped our conversion factor right here, right? And that's because we want atoms on the bottom so that the units work, and so that we can end with moles of aluminum on the top. So we end up seeing that 5.75 times 10 to the 24th atoms is the equivalent to 9.55 moles of aluminum. And really, with enough practice, these types of problems really become second nature. These aren't really problems that you'll see all that much in the AP exam, because it's just dimensional analysis. It's just unit conversion. So it's really applying moles in future concepts is what you're going to see. So we're going to talk about really the most important part of learning about moles and molar mass, which is really the molar mass part, right? We learned about moles. We know that in 1 mole of something, there's this 6.022 times 10 to the 23rd of that thing, right? Well, this really plays in to converting between grams and moles. Because if you know how many moles you have of something, you really know how much of that you have. So really that connection between the mass of something and the number of moles, that's the really important part. Because then you can find, for example, how many grams are going to be produced from a certain reaction, or how much water you have going into some reaction, how much salt, how much whatever reacting going into a reaction, both in terms of the actual amount of substance and the mass. So really, like I said, the molar mass is just the mass of 1 mole of something. And so that's kind of a weird way of saying it. So again, let's go back to our analogy, right? We have a dozen apples and a mole of apples, right? So if we say that a dozen apples has a mass of 4.5 kilograms, that's almost, I like to call it like the dozenal mass, right? It's how much mass a dozen of that thing weighs. So just the same, 1 mole of iron has a mass of 55.845 grams. So that's the molar mass of iron. If you get 6.022 times 10 to the 23rd iron atoms together, you'll end up having 55 and somewhat and 8.845 grams of that iron. And so molar mass is measured in the number of grams per mole, right? Grams per mole. So that's going to be our conversion factor when we're converting between moles and grams. So that's why molar mass is so important, because it really gives us a way to convert from moles to grams and to number of particles in a situation. So really, how do you find molar mass, right? We have this concept of molar mass, but how do we actually find what the molar mass of a certain element is? So molar mass is really, it's found on the periodic table. It's simple as that. That number under nitrogen, oxygen, fluorine, these numbers right here, these are the molar masses of that element. So if you get 6.022 times 10 to the 23rd atoms of oxygen together, you'll have 15.999 grams of oxygen. Similarly, if you get 6.02 times 10 to the 23rd atoms of fluorine together, you'll end up with 18.998 grams of fluorine. And the same thing goes for nitrogen and for any other atom on the periodic table. So for example, let's do a practice problem real quick. What is the molar mass of gold? Right, so pull up a periodic table on your computer. If you go to, I'll drop a website right here, and find for me the molar mass of gold. Right, just head over there and just give me the number, 196.97. Perfect, exactly, right? So if we're finding the molar mass of gold, all we have to do is first find gold on the periodic table. So it's element number 79, and then the number right under it is the molar mass. So what does that number really mean? Right, so drop in the chat, like what from what I've said and from what does that number represent? Why does that number matter? Right? What does that 196.97 grams per mole mean in pertinence to gold? It is the atomic mass of gold. You're not wrong. However, when we're talking about moles, the important thing to talk about is that when you get together a mole, yeah, exactly, Owen. 1 mole of gold will equal 196.97 grams. So really, these numbers, they might look really close to the atomic masses of some of these atoms, right? It kind of starts to fall apart near the bigger elements. However, it might look like that, and that's really due to the fact that Avogadro's number was originally defined as the number of carbon-12 atoms, carbon-12 atoms in 12 grams of carbon-12. So it's built to kind of have this relationship between the molar mass and the atomic mass. However, the molar mass, when we're talking about the periodic table, the molar mass is really the number of the number of grams per mole of that substance. So if we get together 6.022 times 10 to the 23rd atoms of gold, we will have 196.97 grams of gold, right? So let's start talking about how you'd find the molar mass of a molecule, right? If I tell you we have 1 mole of water, that has some weight, right? And so what you do to find the molar mass of molecules is you just add up the molar masses of the components, right? So let's start with water, one of the most simplest molecules out there. It's just H2O. So we know that the molar mass of hydrogen is 1 gram per mole, and that's on the periodic table. And then oxygen is 16.00 grams per mole. I know the periodic table says 15.999, but rounding up to 16, it'll make our calculation simpler, and it really won't impact our margin of error that badly, especially with correct sig figs and stuff like that. So what we do is to find the molar mass of water, we use these molar masses, and then we multiply by the subscripts right here, because that's how much you have, right? So we have 2 hydrogens and 1 oxygen. So 2 times 1 is 2, plus 16 gives us 18 grams per mole of water, right? So that's really, if you get 6.022 times 10 to the 23rd molecules of water together, you'll have 18 grams of water. And this applies to any molecule, ionic compounds, covalent compounds, anything like that. The molar mass will remain the same for that compound no matter what. So for example, here's another one. What is the molar mass of sodium nitrate, right? So the first thing we want to do is just split it up into its components, right? 1 sodium, so we have sodium here, 1 nitrogen, so we have nitrogen there, and 3 oxygens, right? We look down here and we have 3. So we're going to do 3 times oxygen. Excuse me. So then what we're going to do is we go to the periodic table and you find sodium, you find nitrogen, and you find oxygen, and you write in those molar masses, and then you put it into your calculator, and you get your answer in grams per mole. Right, and so you can see this even applies to things like ionic compounds and stuff like that. So it's not strictly covalent, it's not strictly ionic. No matter what, if you have some chemical formula, there is a molar mass for it. Right, so molar mass really, when it comes to the bottom of it, molar mass is a conversion factor. Right, if we're talking what is the mass of 1.25 moles of silver, we can just use the molar mass of silver as as the conversion factor to find the number of grams. Right, and that's the same concept as when before we used Avogadro's number to convert between moles and atoms. So, for example, if I told you, what is the mass of 2.4 moles of sulfur? What would our conversion factor be? Go to your periodic table, find the molar mass of sulfur, and write out with units what the conversion factor would be to convert from moles of sulfur to grams of sulfur. moles of sulfur times 32.1 grams of sulfur times 1. Right, perfect. So what Owen said basically is that for however many moles of sulfur you have, you're going to multiply that by your conversion factor with the molar mass, right? 32 times 0.1 grams of sulfur over 1 mole of sulfur. All right, so let's look at a practice problem. So how many moles are found in 1.67.55 grams of iron? So here you're going to actually have to flip your conversion factor in order to get your answer, right? Because instead of going from moles to grams, or instead of going from grams to moles, we're going from moles. Wait, no. Instead of going from grams to moles, we're going from, instead of going from moles to grams, we're going from grams to moles. Jeez, I can talk today. So just give this one a try. You know, tell me first, how would you set it up, right? Just tell me the setup, and then I can show you the answer. So let's take a look at how you would set up this problem, right? So we start out with our 167.55 grams of iron, just like it said in the problem, right? And so in order to convert this to moles, we want to we want to use our molar mass as a conversion factor. So instead of saying grams per mole, now we're going to say that for every 1 mole of iron, we have 55.85 grams of iron. And that's found right on the periodic table, element number 26. And then by doing this conversion, we find that that's exactly 3.00 moles of iron. And so when you're doing a problem like this, you to make sure that you're using the correct conversion factor and the correct units. Because if you screw something up like units or something, that can be a really easy mistake. For example, if they give you 167.55 kilograms of iron and you just went ahead as if it was grams, you get a completely different answer than if you first did the conversion from grams from grams to moles. So you need to be careful with, you know, what your units are and how you're actually going to handle it. All right, so let's look at so this is our last practice problem. Right? I don't know why it still says practice problem number 1. So what is the mass of chloride, right, Cl minus, in 1.2 moles of copper 2 chloride? Right, so think about this for a second, right? And I'm just going to show the answer right now. Right, we start with 1.2 moles of copper 2 chloride, right? Stating the problem. However, they're asking about chloride, not about copper 2 chloride. So first we have to find a way, you know, how do we find out how much chloride is actually in copper 2 chloride? And that's simply found by looking at the chemical formula, right? If we look, we have 1 copper and 2 chlorides. And so we know that if we get together 6.022 times 10 to the 23rd of copper 2 chloride, we have 1 mole of it, we're going to have double the amount of chloride, right? Because for every 1 copper, we have 2 chlorides. So if we get together 6.022 times 10 to the 23rd copper 2 chlorides, we'll have double the amount of chloride as we will copper. And that's really why the mole is so important, because it can help you look at, you know, the amount of something that you have relative to another thing. So we use this conversion factor, and this right here will give us the number of moles of chloride in 1.2 moles of copper 2 chloride. And then from there, we want to cancel out these units, right, by using another conversion factor and getting to grams finally. So really, this problem here is something that you might see on the AP exam, right? It's definitely less of a just plug and chug answer and more of a, you know, thinking about it and how to actually interpret the problem question that you're going to kind of see on the AP exam, right? Because it requires you to know that you'll have 2 moles of chloride for every mole of copper 2 chloride. And then from there, you don't want to use the molar mass of copper 2 chloride, because we're looking at chloride. So we want to see what's the molar mass of chloride. And you might be thinking, you know, oh, I can't find chloride on the periodic table. it's the same as chlorine, because when you rip an electron off of something, the electron is so ridiculously tiny that it doesn't contribute any mass whatsoever. It's even not even considered to have, it has a mass. It weighs so little that it won't have an impact on your answer. So the molar mass of chloride is the exact same as the molar mass of chlorine. And you end up getting 85.08 grams of chloride. And if you don't understand this problem, it's okay. Lots of practice and lots of just looking through problems and just thinking, how do I do this problem? And you don't even just have to compute it. Just knowing how to approach the problem is really important. All right, so now that kind of finishes up the slideshow. So now I know we see a question from Owen. If you guys have any other questions, drop them in the chat, or just something to say about moles, molar mass, even just AP Chem in general. So let's start answering this question by Owen. All right, so how would you compute the number of atoms of just hydrogen, for example, in 5 grams of H2O? That's a really good question, actually. So I'm going to close out the slides. I'm going to pull up an online whiteboard so that I can start drawing and doing these problems for you live. Right, here we go. So he's asking us if we have 5 grams of H2O. So let me just write that down. And just bear with my handwriting. I'm drawing with a mouse, so it might look a little sloppy. If we have 5 grams of H2O and we want the number of atoms, so we want the number of atoms of hydrogen. That's what we're looking for. Well, if we want the number of hydrogens, the only place we can go from grams is to moles. And then from there, we can find the number of atoms. So what our game plan really is going to be with this problem is going to be, first, find the number of moles of water, then find the number of moles of hydrogen, and from there we can find the number of mole atoms of hydrogen. And so really a good general rule of thumb is that when you have grams and you need to find something else, the only place you can go from grams is to moles by using the molar mass. Let me just take a swig of my water here. Stay hydrated, kids. Get your H2O. So we have 5 grams of H2O. So the first thing, what do we want to find if we want to find the number of moles of H2O first? We simply want to convert from grams of H2O to moles of H2O. What would we use? What would we use to find that? Drop in the chat. Maybe not even the numbers, but what would the conversion factor look like? 1 mole over 18 grams of H2O. Perfect, right? So we have 1 mole for every 18 grams of H2O. Excuse me, geez, I don't know why I'm coughing so much tonight. So I get rid of this. Right. So we have 18 grams of H2O. So now what we want to do is we want to convert from this number, this moles of H2O, to moles of hydrogen. Right. So we put moles of H2O on the bottom, right? Because we want these units to cancel out. So how many moles of hydrogen are there in 1 mole of water? Just give me that number. Is it 1, 2, 5, 7, 11? So 1. So you're saying there's 1 mole of hydrogen for every mole of H2O. Because that's 2. Perfect. Right? So let's look at this, right? If let's look at H2O, right? And maybe this might make more sense visually. When we look at H2O, what that really means is we have an oxygen, right, bonded to 2 hydrogens, right? That's what H2O is. So if we have 1 H2O, we have 2 hydrogens, right? 1, 2. The same is just the same. If I say how many hydrogens are there in 4 H2Os, right? You could draw that out, right? If you have 4 H2Os, you'll have double the amount of hydrogen. Right here we can see we have 4 H2Os, and so now we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Right? The same goes for moles. If I have 1 mole of water, I'm going to have 2 moles of hydrogen. And that's due to the fact that you just look at the subscript and you'll see you'll always have double the amount of hydrogen as you will oxygen. So we see we have 2 moles of H, right, hydrogen. So now we want to go from moles to atoms, and then we'll finally have our answer. This is a really, really multi-step problem. I really like this question. So again, we want moles of hydrogen on the bottom. And so now we want to get to atoms of hydrogen. So what do we use now to get from moles to atoms, right? What number that we talked about that's pretty significant, right? What is that number? And this is a number that you should, I don't know if they give it to you on the test, actually. I wouldn't be surprised if they didn't. This is a number that you should probably memorize. Just, it should be like second nature to you. And so yeah, Sonia has it, right? 6.02 times 10 to the 23rd, Avogadro's number. So I'm just going to actually type it because I'm too lazy to write out. Right, and on the AP exam, they'll give you a specific, I'm sure they'll actually would give you Avogadro's number because you need a specific number of significant figures and stuff like that. And for this problem, we're kind of going to ignore sig figs a little bit because of what we're talking about. And so here's our setup, right? So let's just go through, that was a lot, right? So let's just go through what this all means. So we start out with our 5 grams of H2O, right? So from grams, the only, where's the only, what did I say? Where's the only place we can go from grams? Drop in the chat. If we're given grams, what's the only thing we can do with those grams? To moles, exactly. The only place we can go from grams is to moles. With moles, you can go all over the place. But if you're given grams, you have to go straight to moles. And I would say in 99% of problems, when you're given grams, you're going to have to at one point convert that to moles. So we first take these 5 grams of water, convert that to moles right here. So now we've got moles of water, and then we convert to the number of moles of hydrogen, right? And that's because we wanted the number of atoms of hydrogen. So when we convert to the moles of hydrogen, we make sure to look at the subscript of hydrogen in H2O, which is a 2, and that's the number that goes right there. Because we'll always have double the amount of hydrogen that we'll have for every 1 mole of H2O. So we'll have 2 moles. And then for moles, we want to find atoms. And when we do that, we always want to use Avogadro's number. And I realize here I wrote 20 to the 23rd. That's a 1. It's supposed to be a 1. Let me retype that. That's a 1. It's supposed to be a 1. There we go. You saw nothing. So when we convert from moles to atoms, then we finally have our answer. So let's plug this into a calculator here. I can share my screen, yeah. So close video, and then I will just share my whole thing here. Perfect, right? So now if we go to our calculator, right, so we can just look up like calculator, right? This is where things are going to get tricky. Actually, I'm going to use an online like scientific calculator because you guys aren't going to have like a Google calculator. So you're going to start with 5, right? When you're just putting in numbers, then you're going to divide, you're going to multiply then by 1 over 18, right? Then you're going to again multiply that by 2, right? 2 over 1, and then multiply that by again by 6.02 times 10 to the 23rd. And so we get our answer to be 3.444444 times 10 to the 23rd, which you would then, right, then you would round that down to, if we're looking at sig figs, you would round that down to maybe 3.3 or something like that. I'm not sure of the exact sig figs, but that would be your general answer. You would get something like 0.3 times 10 to the 23rd atoms. Yeah, of course. So that's the thing when you're dealing with, and you can see that makes sense, right? We have 5 grams of H2O, and that's not even half of a mole. And so it's clear that we're going to have less than Avogadro's number of that thing, right? So that really is why we got the answer that we did. And you can always look at your answer and just think to yourself, does this answer make sense? I'll be perfectly honest with you, there were some answers in the AP exam last year that made no sense whatsoever. So it's not the most, valid system, but it's definitely, if you are doing a problem like this and you end up getting that you have, 12 atoms of hydrogen, that's blatantly false. You can look at that and be like, no, something's off. Right. So does anyone else have any questions, comments, concerns, just about AP Chem in general? Let's get away from moles and molar mass, just anything whatsoever about the test, the class, in general. Hang out for another minute or two. If you guys are good, you're good for me to go. Drop in the chat, So if you guys just have any more questions, anything else, feel free. What about calculating percent composition? All right, that's a really good question, right? It's kind of it's pretty related to what we're talking about, right? So if we're looking at percent composition, all right. So if we look at, let me pull this up again. I'm late. Oops. Hi, Sally. Welcome. We're just kind of asking questions right now. So if we go over here, let me pull this back up. All right, so that's the problem from before. So when we're looking at percent composition, excuse me, I'll be honest with you, percent composition was always the one thing I could never remember. But so for example, let's look at this problem, right? Let me copy and paste it right in here. What is the percent composition of calcium oxide? All right, so, geez, I really need to remember how to do percent composition because it's simple, but it's always something I forget. Right, so the mass percent composition of, so by mass of its elements, by mass, okay. That's why I was freaking out because I'm like, is it just by mole? Because if you're looking at it, there's two ways to look at this, right? There's by mole and by mass. So if we look at this by mole, it's 50-50, right? 1 to 1. But if we're looking at it by mass, it could be way different. And so first, let's start with the percent composition of calcium, right? What percentage will be calcium? Well, the first thing we want to do is find the molar mass of calcium oxide. Right, so we have calcium oxide, and we can use the same method that we had before, right? We just do calcium plus oxygen. And then from there, we have no subscripts to deal with, so it's just straight up Ca plus O. So we go to our periodic table, and we see that, and I'm going to really be pretty generous with the rounding, just so I don't have to pull up a calculator. So let's say calcium, it's 40.0, and let's just estimate oxygen to be 16, right? That's going to give us 56 grams of calcium oxide per mole of calcium oxide. And so that's really going to be the big thing. It's really going to be that 56 that's going to be important. Right, so in 1 mole of it, we have 56 grams. Right, and that's where the mass comes in. If we're looking at calcium, the molar mass of calcium, as I said, was 40. Then we look at oxygen, and that's only 16. So we can see that in 1 mole of this substance, by mass, there's going to be a lot more calcium than there is going to be oxygen. Right? Does that make logical sense to you guys? Right? Because by mass, you have a lot more calcium in this molecule or in this compound. Yeah, it's not a molecule, but in the compound compared to oxygen, right? Because in 1 mole of that, you'll have 40 grams versus 16 grams. Drop in the chat if that doesn't quite make sense, or if it makes sense, say that too, just so I can see where you guys are. And then from there, I'll move on to finding the actual percent composition. Understandable. So from here, let's actually calculate it. So let's start by looking just at calcium, right? So let's just start with calcium. So all we have to do actually is just take that 40 grams of calcium, and that's per 56 grams of calcium oxide, right? Because that's really just me saying that 1 mole of calcium is in 1 mole of calcium oxide, right? Because then we're just looking at we're looking for the amount of that substance in the mass of that substance in one bit of that, in one molecule or one compound of that compound. So then this is going to come out to 40 divided by 56 gives us 71.4%, right? So that means that when we have 1 mole of this compound, that's going to be that mole is going to be 70 something percent calcium. And then we can kind of estimate it to be what, 28.6, I think. Yeah, 28.6% oxygen, right? And we found that just because it has to add up to 100%, right? So does that make sense? You know, how to find it, what we did, and how to actually do it. And I'll pull out one more practice problem just because the problem that I gave is kind of simple. And so when we get into more complicated molecules, it could definitely change things. Perfect, right? All good. So now let's do another practice problem where things might get a little bit dicey. All right, so if we are looking at, let's say, you know, what is the percent composition by mass of, let's look at H2O, right? It's simple, but it makes sense for what I want, the point I want to make here. So first, you know, what was the first step? Percent composition in the other way. What do you mean by in the other way? Here, let me just stop this question. You know, can you kind of clarify what you mean by the other way? Like you're saying if we had percent in moles? Okay, yeah, definitely. So let's start with moles then. So let's just cross that out. By mole. Right. So really on the AP exam, the most important one is by mass. But when you're doing by mole, it basically is the same concept. Basically, when you have mole composition, you're basically just looking at, for every 1 mole of this, you have 2, you basically are saying that you have 3 moles of like particles, right? You have 3 moles of just, right? And so we see, because you have, you know, 2 plus 1 oxygen, and so that's where we're going to get the 3. We see that when we divide by 2 moles of H, right, we get that from the 2. And then we have 1 mole of oxygen over 3 moles. And so we know that the percent composition by mole is going to be 66.6 repeating, right, percent hydrogen and 33.3% oxygen. Does that make sense? I know I kind of rushed through that really quickly. But basically, it's just looking at the number of like moles of particles total and dividing by the number of moles of a certain thing. Does that make sense? Again, I know I kind of rushed through that, so I can talk about it more in a bit more detail if you want. So now, and I'll kind of check back to see if you're doing all good. So let's now find the percent composition by mass of H2O. Right, so our first step, just like before, was to find the molar mass of H2O. Right? So now we have 2HO, and that's going to give us 2 times 1 plus 16, and those molar masses again. Sure, okay, then I'll stop. So in more detail, okay. So let's look at this, right? If we have 1 molecule of H2O, right? Let me just cross that out and say mole again. So if we have 1 molecule of H2O, right? Let me just draw this in there, and then I can label these as H and O. So we can see that we have three things here, right? We have H and we have O, right? But three parts, right? 2H plus an O. So if we have 6.022 times 10 to the 23rd of this, basically it's saying if we have 1 mole of that, what percentage of that mole is hydrogen? What percentage of that mole is oxygen? Right. So imagine if we had, 6.02 times 10 to the 23rd of this thing. But let's just first, right. Okay. I'm sorry. When you're talking about composition by mole, it's basically saying that what percentage of this is hydrogen, what percentage of this is oxygen. So let's just boil it down to just first these two molecules, right? We have two H2Os. So first, what percentage of it is hydrogen? Well, we have 4 hydrogens over 6 things total, right? 1, 2, 3, 4 versus 1, 2, 3, 4, 5, 6. So we can do 4 over 6 is equal to 2 over 3, which then gives us 66 or 66.6%. So does that part make sense? And then the same applies if we had a billion molecules, or 6.02 times 10 to the 23rd molecules. You'd always end up getting 2 hydrogens for every 3 atoms, right? Yeah, I multiplied it by 100. Right, exactly. So when you're doing percentages, it always adds like a times 100 at the end, because then you'll get the actual percentage. But really, for example, if we're looking at 2/3, 2/3 as a decimal is 0.6666, so on and so forth, and it repeats infinitely. So really, all you have to do to get the percentage is just move that decimal point over twice, and you'll get 66.6%. And that little bar right there means infinity, right? Then just they're infinite 6s that keep repeating and repeating and repeating. And then from there, once we have the other thing, because we're looking at just 2 things for now, then all you have to do is find the complementing part to find 100. In other times, you might have to find all of the parts using the same method that I just did here. But for now, right, we can then see that, let's actually do that, right? We have these 2 molecules here. So we have 2 oxygens, right? So now we have 2 oxygens for 6 things, right? And so that is equal to 1 over 3, which gives us 0.333, so on and so forth, which is then equal to 33.3 repeating percent. So does that make sense to you now? Does that clear it up? The really important one to understand is percentage by mass. I actually haven't until tonight seen percentage by mole, at least on a practice test or any sort of AP style thing. Perfect. So now let's move on to percentage by mass of H2O. Right? Here we go. So the first step of this, like we said, is to find the molar mass of H2O, which we found a couple times tonight to be 18 grams per mole. Right? So now we want to find basically in that 18 grams, or in 1 mole, let's just start with that. In 1 mole of H2O, right, we have 2 moles, or not 3, I can type numbers. We have 2 moles of hydrogen, right, and 1 mole of oxygen, right? So does that make sense right there? That in 1 mole of H2O, we'll have 2 moles of hydrogen and 1 mole of oxygen. Right, does that make sense just right off the bat? Or have I lost you already? Perfect, right? So now, all we have to do is find the actual masses of this and this, and then put that into 18. So first, what is the mass of 2 moles of hydrogen? Right, so we start with 2 moles of hydrogen, and then we want to multiply that by, as we've done a couple times, what do we want to multiply that by? Right, so we have moles of hydrogen on the bottom, and now just find me the number on the periodic table. Look and find me the number of grams per mole of hydrogen. Right, so if we look on the periodic table, we can see that if we look at hydrogen, right, and we see right under the hydrogen, we see 1.008. That is the molar mass. Perfect. So just for the sake of simplicity, I'm going to round that down to 1.0 grams. If you want to be super precise, no, you're right. You're right. 1.008 is the correct answer. I'm just going to round it down for the sake of simplicity here. But you're not wrong. If you did this with that number, you would be perfectly correct, and you would probably end up getting an even more correct answer, actually. But just for now, just so I don't have to use a calculator, I'm going to use 1.0. And really, for the sake of all your calculations in the future, you can estimate hydrogen to be 1 and, you know, nitrogen to be 14, like that. It's when you start getting to like things like lithium, you can't say 7. With lithium, you kind of have to say 6.94, or magnesium, you have to say 24.3. That's really where it starts getting, you have to use the decimals. But things like oxygen and stuff like that, you typically can make it 16. And so that's going to be 2 grams of hydrogen, right? Does that make sense? How we did that? I feel like I'm just asking that 150 times, but yeah, just making sure that y'all are right. Okay. So now we actually don't. Actually, let's do it. I was going to say something, but let's just do it. So we have 1 mole of oxygen, and from there, we're going to multiply that again by its molar mass. So as we said before, that's 16 grams per mole of oxygen, and that's going to give us, just multiplying by 1, 16 grams. So that's the bulk of our work. Just finding the, you know, this part was the really important part, and that's why I brought up this problem, because before, when we were dealing with calcium oxide, it was 1-to-1, whereas here it's not proportioned out the same, right? We have more moles of hydrogen than we do oxygen. So now what we want to do is do the same thing we did before, right? With hydrogen, we have 2 grams per 18 grams of H2O, right? Grams of hydrogen. And so that'll be 1/9, I think. Yes, which is equal to 0.11 repeating, which gives us 11 point, and I'm just going to say 1%. All right, so there's how we found hydrogen. So now we want to do the exact same thing for oxygen, right? So we have oxygen is equal to 16 grams per 18 grams of H2O. Right, so you can see, even though we had more moles, you know, the mole composition of this implied that we had 2/3 hydrogen and 1/3 oxygen. But here, it's implied that we, you know, by mass, only 11% of this is hydrogen. So that's the importance of really, you know, you can't look at this and be like, oh, there's going to be a ton more hydrogen in here. By mole, yes, but by mass, you know, if we do 16 divided by 18, that's what? That's 0.88. That's 8/9, right? Is equal to 0.88 repeating equals 88.8%. Right, and you know, you would end up, if you wanted to do this problem with that relative amount of sig figs, you would want to round it up to 0.9, right? So 88.9%, but it's just a matter of making it, you know, add up to 100. So that's really how we did that problem. So that's really how you do percent composition with anything in AP Chem. And it's really important to be able to understand things with moles because of problems like this. If you don't understand moles and molar mass and the stuff we went over tonight, a problem like this is basically impossible, right? So it's really important to do lots of practice if you're stuck on stuff like that, to do lots of practice. Right. So you guys have any more questions, or are we good? You know, if you, here, I'll drop maybe some of my, you know, if you guys want, I can put in some of my social media and stuff if you want to keep asking me questions and stuff. Yeah. All right, looks like we're good for tonight. If you guys have any more other questions, and just be sure to, there are a ton of resources out there, a ton of different types of things to use to make AP Chem. Definitely, it's a very difficult class, so try to make it as easy as possible on yourself. So I'll end this here. I'll see you guys whenever I see you, and I'll talk to you guys later.